Som, can you start?
Yes, sir.
Good afternoon, everybody. First of all, thanks for sparing the time for this webinar. In fact, we are privileged to have with us our Additional General Manager, Mr. Sumit Jain from RVNL, who has really taken out the time from his busy schedule to give his expertise and his experience about the underground construction and shotcrete technology. I just brief about him. He will be taking the 20 slides from the total of the slides, but he has got around 1 point. He's a civil engineer, passed down in 2005 from Delhi College of Engineering. Has got 1.5 years of experience at NTPC in hydro engineering as an engineering, 6 months at Coldam for the site execution, and 6 months at the design cell of NTPC on Lahori Nagpala. So practically he has got experience in all the fields, I would say, from design to the execution stage. And after that, he has worked for 6 years with the prestigious Indian Railway Mass Organization with the various capacities of assistant executive engineer and track, bridge maintenance, construction of new assets, approximately 400 kilometer section. With 7 years, he has been working with RVNL since 2013 and has contributed towards the development and planning of the project from the feasibility to the execution stage. And currently, he is studying various tunneling practices, contractual setups prevalent in various sectors in India, study and option of foreign tunneling standards, guidelines, and practice to enhance the productivity and the life cost cycle of the tunneling works, and preparing technical and contractual framework for the tunnel construction and consultancy works. Design and construction contract procurement for RVNL and field execution. Apart from that, I would say he's heading, or he's quite actively and aggressively involved in the project which is in Uttarakhand, for which he will be giving a very short synopsis about it and new technology, what he has encountered and how he has handled it. Apart from that, from Mapai, we have Michaelis Davide, who is a technical support working with Mapai from last almost 10 years. He's a master in science in geotechnical engineering. From the start of the career, he has been working with Mapai, heading the technical services for the UTT. UTT is basically underground technology team for the Mapai, which is a team which has been focused for the underground construction. And we have got this UTT team across the globe for the specialized underground constructions in a particular country, and has got product line for conventional excavation methods, products for the TBM, for drill and blast. And Davide Michaelis has been quite instrumental in supporting the India, which he will just give a brief about. He has been coming to India from last 10 years. He has got experience in traditional tunneling, products expert involved in several tunnel projects worldwide, boring, trenchless technology, wide knowledge and expertise. After that, I just hand over the presentation to Mr. Davide, and we will be covering some part of the presentation, and after that Mr. Jan will take over. And then in case of any question and answers, you can either write in the chat box or you can send us to mail also. So we will be pleased to answer the questions at the end of the presentation. Thank you. Over to Davide.
Good afternoon to all of you. Thank you for joining this webinar. First of all, I want to thank Mr. Sumit Jain for really his strong willing in organizing this webinar, and of course, technically speaking, for his incredible focus on trying to and succeeding in getting a higher quality in underground sector, especially for shotcreting. Thanks also to Sanjay for the introduction, and to our colleague Subodh Nene, who has organized along with Sumit all the webinar. So today we will focus and we will stay together for about 1 hour in focusing on shotcrete technology for underground construction. This will be the main main arguments that we are talking about today. So about the history and the recent developments of the technique, the ingredients, the specification, and the mixed design for a shotcrete, pre-construction controls, pre-construction controls, production controls, so keep focusing on constituents, mix, and of course on the sprayed panels during the testing sequence. We will have a deeper look on the application control, equipment, and one of the most important factors, which is the operator skillness in spraying the shotcrete. We will also have the chance for Sumit, with Sumit, to highlight an experience for a Rishikesh project. And finally, we will have a moment for question and answers. If you have any doubts, please write on the proper box, and then we will try to answer as many questions as possible. So, starting from a bit of history about shotcrete, going back to the 70s, where the dry mix process was especially accelerated with alkaline powder accelerators. So we are really at the beginning of the technology employed inside a tunneling project. In the 80s, there is an introduction of powder microsilica in order to have a better mix design and extend the durability of the mix design. Then at the end of the 80s, we are looking inside the introduction of alkali liquid accelerators. So they are replacing the powder one, especially in the dry process. Changing from the 80s to the 90s, we are observing the first wet mix process, which is of course the base of our actual technology, which is almost employed all over the world. In the 90s, we have the chance to extend the performances and getting a high performance wet mix process because of low dosages of liquid accelerators. And we are looking also to the use of steel fibers to enhance the flexural strength of the shotcrete. Then later in the 90s, almost in the new century, we are looking for new alkali-free accelerators. So the technology about the accelerator is changing dramatically, and with the use also of microsilica slurries, of course, to extend the durability of the final product. Steel fibers also are enhancing their properties, and the way of application is improved. Luckily, also with the use of very powerful plasticizers, we can face water cement ratio below 0.45, which we will see later in the presentation is an extremely interesting point for having a high quality shotcrete. And we are passing from a manual application to a robotic spray system, which are giving the production rates that we are having today. Nowadays, we are looking to, and we are succeeding in getting mixed designs with water cement ratios below 0.4, and also the use of synthetic fibers, structural synthetic fiber, is spreading around. So we are having very good results also with the use of polypropylenic fibers. What's in the future? Hopefully, and also looking for a higher production rate. Of course, we need higher outputs, but of course also enhancing the properties of the shotcrete in order to have a proper thickness applied on the shotcrete surface, and of course a proper strength development in order to get a faster setting time and reducing also the problem in presence of high water inflows. Just some nice pictures coming from the past. On the top left, you are looking to maybe one of the first dry shotcrete machines. It's a picture taken in the 1907, so more than 100 years ago. And you will see bottom left Mr. Carl Axley, which is one of the founder, one of the first men to use shotcrete as an industrial process for underground construction. As you can see also in the other two pictures, how difficult was the application, especially overhead of the shotcrete. So it was needed to build up scaffolds and using, let me say, not very automatically driven equipment. And of course, if we compare with the new equipments that nowadays are available on the market, we can understand how higher could be the production rate, how bigger and nicer could be the quality of the shotcrete that we can produce in our time. So let's start with the ingredients which compose a proper mix design for a shotcrete application. First of all, we have to, of course, it's running. The cement is, of course, one of the most important parameters and product that we have to consider for a good mix design, especially talking about the fineness of the cement. Then we have to, sorry, it's not moving. Okay, aggregates, different shape. It depends if it is crushed aggregates. It comes from a riverbank. Water, of course, we need to put water, especially tap water, as much as possible in order to get a high quality mix design. Admixtures that are both to be placed inside the mix design during the production process, and also like the accelerators to be introduced in the mix design during the application, right at the nozzle before the product flows out from the boom of the spraying machine. We can also add, and sometimes is absolutely mandatory to use mineral fillers like silica fume, microsilica, in order to reduce the water amount and increasing final strength and durability of the final product that we are applying on the surface. Fibers, as introduced before, can be both steel, plastic, and we will see later which ones. And this is an additional product that is enhancing the flexural strength of the product. Cement. Of course, cement. Not all the cement are proper for the use with a shotcrete mix design. We have to think about what kind of mix design. For example, we need a pretty high fineness of the cement, 350 square meter per kilo, and we need a minimum amount of OPC of 360 kilogram per cubic meter when we start to design our mix design. As a rule, general rule, but it's depending a lot on which kind of country we are deciding to design the mix design. The minimum cementitious content is varying in between 390, 450, in some situations even higher, depending on performance required and on which kind of cement is considered for the mix design. The cement type, of course, influences a lot the performances. not only the final one when the shotcrete is hardened, but especially during the also during the workability and the fresh status of the concrete. And remember that each recipe is unique, so we cannot reply all a single mix design, doesn't matter where, because the performances will change a lot according to the cement kind, cement type, kind of aggregates, and kind of admixture that we decided to put inside. One recommendation is to, anyway, avoid high cement content, because in case the cement content is too high, we could have shrinkage and thermal cracks that, of course, are something that we want to avoid to have a proper final product. Water, it's along with the cement, I think the most important component to be properly dosed and used, because of course we need to use tap water. This should not have any chloride and sulfate and oil inside, but especially the content inside the mix design should be as much as possible lower than 0.45, because the quality of the shotcrete will rise a lot in using a low water cement ratio. Of course, the ideal range is in between 0.38 and 0.42, and with these values we can achieve, of course, high strength and durable shotcrete, but also during the application sequence we can really reduce a lot the rebound. We can face even difficult situations like water at the tunnel phase. To achieve these low water cement ratios, we can use superplasticizers and retarders, which are enhancing the workability and the open time before the application take place. And of course, we have to consider which kind of admixture superplasticizer in order to avoid any wrong effect on the setting time of the product. Then accelerators, of course, we have to add the accelerator right at the nozzle of the spraying equipment in order to accelerate a few seconds before the shotcrete hit the surface of the substrate. Of course, adding the accelerator to the nozzle, it's causing a drop of the final strength compared to an accelerated mix, and this can be up to 70-75% of the unaccelerated mix. But consider that with the alkali-rich accelerator, the drop is not only 20-25%, but we can even achieve 50% of the drop. So it's very important to also to select the right amount of the right accelerator. This is a scheme that I love to use, because it shows really the concept of water cement ratio. On your left side, you see a low water cement ratio mix design, and you see that the components, the aggregate and the cement are pretty close between them. So when there is the hydration process of the cement, there is a better connection between all the components. On your right side, you see a high water cement ratio mix design, and you can understand very well that it's it's really more difficult for the cement to connect all the particles together. So we are facing a lower strength and, of course, a higher porosity and permeability. This slide shows a standard cement heat curve, for a standard unaccelerated mix design. So you see that there is a stage 1. I think that you see also the pointer. The stage 1 where there is a sudden increase of heat generation due to the start of the reaction of the cement. And then, let me say, an induction period that it can last 2 to 5 hours, depending on what kind of cement we are using. And then, again, an increase of heat generation between initial and the final setting time. What we want to do with the accelerator is to reduce as much as possible this induction period. So bringing the initial set as close as possible to the initial stage 1. 4 pictures to understand to a microscopic level what happens to a cement paste. All the pictures are taken 4 hours after mixing. Top left, there is the reference mix. You see that after 4 hours, there is a start of connection and links between cement particles. You see some shapes connecting the cement particles. Bottom left and bottom right, you see what happens with the same reference mix with sodium aluminate and water glass accelerators. You are looking that there is a different shape of the connections, but nothing that could be compared to the picture top right that is taken with the reference accelerated with alkali free. You see that the connections and the structure between the cement particles is extremely better with the alkali free accelerator. There is a known structure. Instead, for sodium aluminate and water glass, there is something that cannot be defined as a proper defined structure between the cement particles. Aggregates. This is in terms of weight, it's the most important component. It's necessary to keep the aggregate size lower than 10 millimeters, because if we exceed this amount of size, there could be a big rebound. So you lose money and you lose material when you apply the Shotcrete. And it's absolutely necessary to check before the use the alkali aggregate reaction in order with the admixture that are used inside the mix design, in order to avoid this phenomena that is absolutely really risky and with damages for the structure. You see on the right image the FNARC scheme that gives us some indication on which part of for each size of the particle we can keep. For example, for 0.5 millimeter, we have to keep in a range of between 22 and 50% of the passing. There are also some mineral fillers, so as additional ingredients. As a rule, we should not exceed 15% of the OPC, and this should have a silica content, amorphous silica content higher than 85%, and a very high specific surface in order to be kept inside the mix design in a proper way without any bleeding problems. Of course, the compatibility with accelerator must be checked before any qualification process. What's the aim of putting mineral fillers? It's to, we said already before, enhance the early and long-term strength and durability. And of course, it enhances the adhesion of the mix design during the spraying sequence. Fibers, it's another ingredient. We can find structural and non-structural fibers. focusing on structural fibers, there are mainly two groups, steel ones with a dosage that can vary from 25 to 40 kilogram per cubic meter, and the macrosynthetic fibers whose dosage depends, can vary between 4 and 7 kilogram per cubic meter. So there is a big difference in terms of dosage, but very interesting in terms of performances. The non-structural fibers are mainly used for anti-spalling phenomena. So, and they are used in a dosage in between 1 and 2 kilograms per cubic meter. Just a few slides. I think that most of you already have as a good experience for steel fibers, hooked, glued together. In some situations, there are also the use of glass fibers, but it's really a very small area. Synthetic fibers, as I said, it's gaining market against the steel fibers with very good results. And I want to complete my part of presentation just giving some tips about application methods. Most of the application is made with a wet process, but still sometimes there is need for applying the dry mix method. So this slide shows in a very schematic way how it works, the system. So there is inside the hopper, the dry mix is put inside. On the left side, the compressed air pushes the material through the hose, and at the nozzle, and only at the nozzle, water and the accelerator is introduced in the flow in order to get the proper acceleration of the mix design. On the other, so this is the kind of normal application, and an example of the way the workers are doing the job. Of course, this can be used only for small surfaces, a very confined space where a big boom for automatic spraying is not able to enter. On the other way around, this is again a scheme of how it works. So the wet mix is poured inside the hopper, and the pistons are pushing inside the pipe the concrete at the nozzle. Only here, compressed air is added to the nozzle along with the accelerator. The accelerator is dosed according to the different situation we may face, depends if overhead or on the sides, and we are getting the final shotcrete that it's sprayed against the substrate. Okay, so I pass the microphone to Mr. Sumit, and see you later for question and answers. Thank you.
Thank you, Davide, and welcome again to all the participants. So we'll be carrying on forward with the pre-construction controls. And as you are aware that before qualifying any shotcrete, we need to control the quality of the shotcrete before actually applying in the site. So there are some mandatory pre-construction tests defined in the European norms 144871, and we refer to the class 3, which is the inspection category defined for the underground traffic, railway tunnels and road traffics, and the strengthening of the ground is the class which we are referring. So there are a number of tests to be carried out, like the consistency of the wet mix, early stage strength development test, then the compressive test, then the flexural strengths, residual strengths, energy absorption capacity, and the fiber content. So if we see, the first 4 of these tests are for the plain shotcrete, and the later 4 are for the fiber reinforced shotcrete. So the type of test will depend on the type of application and the functional requirement of the shotcrete. Now we will cover some of these tests in brief. This one is the early strength requirement for young age shotcrete, and normally there are 3 classes as per the European norm. So class J1, J2, J3, and Usually we are referring to the J2 class when we are applying in thick layers, including the overhead applications, and there is a very high output requirement of the shotcrete. There is a very low water pressure and the load on the newly sprayed concrete from the subsequent works. So when we qualify a shotcrete as a J2 class requirement meeting, then all the strength results, you can see my pointer, have to be falling above this J2 line. So this is a plot of the compressive strength versus the minutes and time in hours. And for the initial up to 2 hours or say less than 1 MPa, we are using a penetrometer, and more than 1 MPa, we are using the Hilti shotgun method to test these early strength requirements. And mostly the shotcrete strength should start very near to the J2 curve, and by the end of 1 day or say 24 hours, it should actually reach right up to J3. So this is somewhere around 12.5 MPa or 13 MPa maybe, and within 1 hour it should be having a 0.5 MPa strength. Next is the residual strength requirements. So again, the drawing, the figure shown on the right side is a 4-point bending test. Here the beam specimen is prepared with shotcrete, and then it is tested in the standard apparatus, and the categorization of the class is done by the deflection and the strength of the residual strength of the specimen. So for example, these are the categories defined in the European norm. So there are 3 deflection levels and 4 strength levels. So if we qualify shotcrete to be D2S2, then it should have a minimum residual strength of 2 MPa in the range of 0.5 to 2 mm deflection. The deflection is measured in mid-span of this test. And we'll just see a graph, how the graph plots when we are testing this specimen. So this is the graph plotting, and as you can see, it is the strength is gradually decreasing with the increase in deflection. So in the area between 0.5 mm and 2 mm for a D2 categorization, this graph should lie above 2 MPa. This is the 2 MPa line, this is the strength class line, and these are the deflection class lines. So in this case, the graph which is plotted for stress, residual stress versus deflection, categorizes for a D2S2 class, because all the part of this curve is lying above 2 MPa. Then moving on to other requirements, in some projects we are using Q support system, and there is a requirement of energy absorption values to be met before qualifying the shotcrete for various Q classes. So this is a graph showing the Q value, rock mass quality versus span or height by ESR ratio, and this is a very well known graph. And here you can see in the bottom left corner in the green highlight, we have a different classification of the energy. So 3 classes are defined: E500, 700 and 1000. These are the joules which the apparatus, which the absorption is there in the panel when it is tested for 25 mm deflection. So we'll cover more on this in the later slides. This is just a fallback of the previous test. So these can be done on circular panels as well as on the square panels. So circular panels are tested by ASTM standard C155019, and we can see there is a plunger which is pushing the panel in the center, and the panel is held at the bottom at 3 points. And this is the typical star crack pattern which we get. As the load increases, the deflection occurs and the crack opens up, and the fibers which are joining the opposite side of the crack, they come into action. Same test we can carry out on square panels. So this is a test apparatus for square panel, and this is the European norm 144885, and these are the typical star cracks which we see in the square panels. So depending on the regulation, we can use either of the tests. Now this is again connected to the previous slide. So this is the typical graph on the left hand side. You can see a load, instantaneous load versus instantaneous deflection curve. And on the right hand side, you can see a cumulative energy versus instantaneous deflection curve. So for example, if we talk about 6 mm deflection, then the energy, then the area under the graph shown in the yellow portion, that is the cumulative energy absorbed up to 6 mm deflection, and that is shown by a red dot on the right hand side of the other curve. So at this point, at same deflection, we have a 200 joule absorption up to 6 mm deflection. So when we are doing the test, both these curves are getting plotted in the apparatus. Now this is same as the 4-point bending. There is another test called 3-point bending test. This is also carried out on a beam specimen. And here we are actually measuring the mouth opening displacement. So there is a notch which we are creating in the specimen, and we are tying a clip gauge to that notch. And this clip gauge actually measures the opening of the crack or opening of the notch as the loading is coming from the top. So you can see a loading pin at the top. This loads the specimen, and the crack generates and travels up to the loading point. And this distance or gap between the notches, this starts to open up. So the opening up is measured versus the load which is being applied. Now this is the graph plot which is coming from the 3-point bending test. So under the 3-point bending test, we are defining the class of Shotcrete by a simple number and an alphabet. Now let me tell you, the number in the first case is the SLS residual stress which is required by the designer, and B categorizes the ratio of the ULS residual stress versus the SLS residual stress. So these numbers are coming from FIB model code. FIB model code is a well accepted code. You can see an image of the code on the bottom right of the slide. And in this test, the 0.5 C mod relating to 0.5 corresponds to serviceability limit state, and C mod corresponding to 2.5 corresponds to ULS limit state. And the respective values on the load correspond to the stresses. So this is the limit of proportionality, which we call FL. FL is computed, and then we get the flexural stress corresponding to FL. Then we get the flexural stress corresponding to SLS state, which we call FR1, and then we get the FR3. So the ratio of FR1 upon FR3 is actually the ratio of SLS by ULS by SLS. And this is the FLS is FSLS, which is 3 MPa, should be more than the SLS stress. Now also, as per this FIB model code, there is a guideline saying that FULS, which is the ultimate limit state residual stress, divided by the limit of proportionality, should be more than 0.4. So basically, this FR3K upon FL should be more than 0.4, and R3K upon FR1K should be more than 0.5. So if both these criteria are met, then we can in a way replace substitute the normal reinforcement like the wire mesh with the fiber reinforcements. Now we go to the production control. So once we have established that the pre-construction, we have put all the controls in place and we have qualified the Shotcrete. So then we have to qualify the constituents, and we have to qualify the mixes, and we have to qualify the sprayed concrete as well. So when we come to the constituent materials, we have to qualify cement, admixture, additives, fibers. So as per the standard, the inspection category 3 of the European norm, each delivery of these constituent materials has to be checked from the inspection certificates. And when it comes to aggregates, the first delivery from the source has to be checked, which includes sieve analysis and other tests like impurities and alkali aggregate reactions and other things. Next, we check the basic mix. So this we check the water cement ratios, and these are to be checked daily when the production is started. So whatever is mentioned in the mix has to be achieved in the batching plant. And then we control the basic admixture, additions, fiber contents. These are recorded batch wise in terms of quantity. Then next we go on to the control of sprayed concrete. So control of sprayed concrete, there are various stages of shotcrete. In the initial young stage, which we also call the green shotcrete, the water cement ratio is calculated daily. The accelerator is daily, and the fiber content, we are doing one test every 100 cubic meters or 500 square meters of sprayed application. And in the fiber content, the individual sampling should have fibers not less than 90% of the target fiber dosage. Next, we move on to the hardened concrete. So previous one was the fresh stage. Now we have the hardened stage. In the hardened stage, we have early strength, which we discussed earlier, like up to 1 MPa by penetrometer, 1 to 16 MPa by Hilti shotgun method. And the frequency of this early stage strength is one test every 250 square meters or minimum 2 tests per month. Now, when we discuss the frequency, we should always bear in mind that this frequency relates to a particular category of inspection and a particular category of application. So this application is ground strengthening and the category is 3. Category 3 refers to the importance of the structure, and ground strengthening is actually the application which we want to perform. Then we are doing the compressive strength test. So here we are taking out cores from the panel as well as from the shotcrete applied wall or the slope. And the frequency is one test every 250 cubic meters or 250 square meters. Then we have the bond strength. So bond strength is a very crucial parameter in this qualification. It really refers to the bonding between the shotcrete and the substrate on which it is applied. If we don't have a good bonding, the shotcrete will simply separate from the substrate and it will fall off in case of any deformations or so. So usually the bond strength in a range of 1 MPa is defined in the standards, and one test has to be performed every 1250 square meters. We are not going into the details of the method, so one can refer to the European norms to have the actual test method and procedures. Now we come to the fiber reinforced sprayed concrete. So here we are testing one test every 100 cubic meters or 500 square meters. And the tests are performed when the age is 28 days. So in 28 days, 3 tests are performed: residual strength, energy absorption strength, and the ultimate and first peak flexural strength. So there is a certain criteria to be met for residual strength, like the mean value of 3 tests and the individual test limit should be meeting the 90% of the target strength. And same for the energy absorption, 2 of 3 panels should satisfy. Now this is all coming from the European norm. So this is a regulation. These are some of the photographs for the production control. On the top right, you can see 2 engineers taking early strength by a penetrometer on a freshly sprayed shotcrete panel. The second image on top is the borehole, the image of a borehole when you extract a core out of that borehole from the tunnel wall. And the central image at the bottom is the core which was extracted from this borehole. And on the right top corner, you can see comparison of 2 cores. One core is having a very poor compaction. So this usually occurs when the pressures, the compaction pressures of the machine are very low, and this is not going to give you any strength at all. And this is a good compacted core, which we can see there is no imperfection and everything is smooth. At the bottom right corner, you can see samples which are having a lamination effect. So we're going to discuss this in the next slide, why this happens. Now we discuss the lamination effect, why it is happening, and we have also entered into the application control. So application control is a very important parameter of shotcrete sprayed concrete application. And the equipment should be very efficient and up to the mark along with the operator skill to have a very good quality of shotcrete. Now, as Davide discussed last time, he showed you an image where two pistons were going up and down to push the concrete into the nozzle. So there is a double acting piston in which the concrete is getting pushed. And when the piston changes from one to the other, there is a sudden drop in the flow of concrete, whereas there is no drop in the flow of accelerator, because accelerator is added at the nozzle and it is added through a separate pump, but concrete is added through a different double acting piston pump. So there is a drop in the concrete and there is no drop in the accelerator. So here you can very well imagine whatever concrete is going here has a very high accelerator dosage and it is going to burn. So these are the burning marks which you can see in black. These are the burning marks where the accelerator is actually more compared to the design dosage. And these marks give a very poor impact on the quality of the shotcrete. So we recommend to use equipment which is having a very low pulsation in the concrete flow. So when the pulsation will be low, by low pulsation we mean the pistons are getting switched very quickly with each other. So when the pulsations are low, the layering effect goes away, literally. So we get a very good homogeneous sprayed concrete. Next, we come on to the equipment parameters which are required. So we need to control the flow of accelerator, which is very important. And concrete flow based dosing system should be used for dosing of accelerator. So when the concrete is flowing, only then the accelerator should flow. When the concrete is stopped, the accelerator should also stop. So this will help you maintain a good dosage percentage and accuracy for the shotcrete. And then there should be a PLC control of the dosage entry. Then we have a good boom. Good boom is always a welcome for the machine. It gives you very high flexibility in movement and allowing a perfect spraying pattern. So as you know, the spraying is usually done in small circular motions. So if there is a rigidity to rotate the boom, then the pattern will not be achieved. And then of course, for the ease of operation, we should have wireless robo control, and lancing should be there. So lancing is basically a mechanism in which the distance between the nozzle and the wall of the tunnel or the slope is maintained at a constant gap, constant distance. Then we should have a very high spray pressure up to 7 bars for good compaction of the sprayed material, else you get a poor compaction in the shotcrete. We should also have a high pressure water scaler on the machine. This is used to prepare the rock surface. Sometimes there are certain hydroscaling requirements at the tunnel wall. So with a high pressure, you can chip off certain loose rocks attached to the substrate. And then of course, data logging of applications is a must to check what are we actually doing inside the tunnel. And last but not the least, FNARC certified nozzleman is the best way out to ensure that the operator is really skilled. Now we cover the important aspects of rebound. So rebound occurs when we are applying shotcrete, and there are various reasons why this rebound occurs. So first one is definitely the nozzleman's skill and experience. Highly skilled and experienced nozzleman can avoid large rebounds. Then the spray direction has to be planned when you are applying. So up direction and down direction give you different rebounds. Then the spray parameters also affect your quantity of the rebound, and the mix design is one of the factors. If you have a poorly graded aggregate, then the rebound will be more. And then what accelerator you are using, how much is the dosage, all these things affect the mix design affects the rebound. And then there is the concrete performance requirement, early strength and thickness of the application and substrate conditions. If the substrate is uneven or there is a lot of water coming out from the substrate when you are spraying Shotcrete, then that will result in more rebound. Now, efficient application usually can control the rebound within a range of 5 to 15%. So if your applications are within this range, then it's a good job done at the site. Now I'll just, this is a brief of the project where I am associated right now. And just let me tell you very briefly about this project in a minute or so. So this is a new line project, and this is done by Rail Vikas Nigam Limited. We are a ministry, we are a PSU under the Ministry of Railways, and we are here to make this project to connect the trade centers and increase the tourism and decongest the road networks. On the right, you can see a India-China map. So we have a black international boundary, and the red line is the alignment of the project. So this is the alignment of the project. This is the international boundary, and this is the location. This state is called Uttarakhand, and you can see the terrain is highly rugged in this area. So coming back to the project, the total length is 125 kilometers, and the length of the tunnels is 105. So almost 84% of the project is underground, and adding the escape tunnels and other tunnels, we are having a total tunneling volume of 218 kilometers, and the maximum tunnel is 15.1 kilometers long. So here in this project, on this package for the adits, we have carried out elaborate testing for the energy absorption for 700 and 1000 joules. So we were following the Q support system chart on this project. So this was the apparatus which we had on the site, and we were testing panels right at the site for all the pre-construction and production controls. And this was tested as per the European norms 144885. And you can see on the right side of the image, there is a, this is the LVDT, which measures the displacement of the panel. And this is the plunger, central plunger. This is 100 by 100 mm. And this measures the, this actually loads the specimen at the center. And this, here you can see there is a display control. So all the graphs and everything is instantaneously displayed on the monitor. And you can, after the test is over, you can actually get a printout of what you have done. So these are some of the images we have tested. The first image is showing the load which is gradually applied on the panel. And when the load is applied, this is the instantaneous load curve. And this is the cumulative energy curve. So two curves are getting plotted simultaneously. So up to a displacement of 7 mm, the things are moving on very well. We have 2-3 ups and downs. And now as we have reached 20 mm, here you can see the panels are getting uplifted. So all the 4 corners of the panel, they actually uplift because the cracks have started forming. And you can see this, the panel has left the apparatus. And this graph corresponds to this image. So we can see a ductile behavior because this panel is having fibers in it. And the energy is gradually increasing. Now, more careful study of the graph which we carried out, we observed that the 3 peaks, the 3 falls in the graph, they correspond to the cracks. So this red peak, when the load went down suddenly, this was the first crack which was appearing. The orange, this one reflected this crack, and the yellow one was this one. And you can see initially the load is building up along with the displacement, and the curve is really smooth. There is no waviness in the curve. So we can say that the concrete was taking all the load. Then the first fracture happened. Then again things started building up. Now you can see slight waviness in the curve. So these are fibers which are getting into action. Now they go to a particular limit, then again there is a drop. Again they rise up, again there is a drop. And this is the place actually where the displacement is now increasing much more at a much more rate compared to the load. So here you can see all the waviness in the, this is actually the ductile behavior has started in the specimen. So these are fiber in actions as the fracture width is increasing. These are some of the site photographs. The purpose is to emphasize that the more the testing is carried out, the better and quality will be achieved at site, and the more confidence everybody will have with the work being done at the site. Now this is just showing you image of the edit 3 which we got achieved at the site. So this was after carrying out all the tests and everything as per the European norms. So this can be achieved very well if we are really want to achieve it. Also, we studied this adding of the microsilica in the Shotcrete mix. So this one is without the microsilica, and this was the contractual requirement. We had mentioned 450 kgs of cement, and we added 27 kgs of accelerator, and we got an energy absorption of 124 joules with a 28-day core strength of 44 MPa. The moment we added silica and we were able to reduce the cement to 385. Now see the interesting change. We have added 15 kgs of microsilica. We reduced the cement by almost how much? 50 and 15, 65 kgs. We have reduced the accelerated dosage by 7 kg. So all this is being saving. This is money saved. And still the energy which we are getting is more than what we got earlier. So this clearly establishes that adding of microsilica actually enhances the durability of the Shotcrete. Because of a good mix in the hardened state, the fibers are really playing their role. And even the COV, the coefficient of variation, was very less. It was only 3%. So we were able to replace 65 kgs of OPC by adding just 15 kgs of microsilica. And this was corresponding to M35 E 1000 joules. Some observations from the field testing of Shotcrete which I want to share, which I gained from this site. The strength of the Shotcrete depends on the mix, machine and applicator. It's not a very straightforward as we think concrete is. So even if you have the right mix, the right machine, but the application is not there, then you won't get what you wanted to achieve. Addition of accelerator gives early strength. Yes, it gives you early strength, but it sacrifices the 28-day strength by almost 20%. So whenever you are going in field trying to establish a design mix, always target a strength of 20% more when we are doing the unaccelerated concrete cubes. So say you want to do a M30 Shotcrete, you want to prepare design mix for M30, you target for M40 without any accelerator. The moment you add accelerator, it will go down automatically to M30. So this is a very important aspect which has to be kept in mind. Then one should avoid a very high cement dosage in the basic mix because it incurs shrinkage and thermal cracks in the tunnel line. And one should be aware that in situ cement dosage is always higher than what you have designed. Supposing you are using a dosage of 400 kgs of cement, in situ dosage will be more than that, because when you are applying the Shotcrete, most of the aggregates are getting rebounded, but the cement stays in its place. So the dosage actually in situ is very high. Then we can definitely reduce the water, and by adding microsilica, silica fumes, they enhance the durability, which we have seen. And the fiber dosage play a very key role in panel energy absorption. So the higher the dosage, the good the absorption energy you will be getting. But please keep in mind that good Shotcrete strength and durable mix is a must to have this rule as an acceptable rule. Otherwise, if you don't have a good strength Shotcrete, if you don't have a durable mix, even adding fibers will not help you. So these are the prerequisites for a good energy absorption in the panel. Then fiber dosage in the design mix forms the design basis rather than the in situ fiber dosage. Actually, this is the same as the aggregates are getting rebound, the fibers also get rebound. So as per the European norms, when we want to check the fiber content taken into the tunnel, inside the tunnel, So one should measure the fiber content right at the pouring point, not at the application point. Now at our site, we used 6.5 kgs of PP fiber. We achieved a maximum of 1500 joules at a 0.37 WC, water cement ratio. But the same thing dropped drastically from 1500 to 900 joules when we increased the water cement ratio to 0.42. And this was only at a marginal reduction in PP fibers. We were still using 6 kgs, which was not very less than 6.5 kgs, but the energy really went down. Next, for the fine cement, like we are using OPC 53S at our sites. So 53S is a special cement which is much finer than OPC 53. And we got a very high energy absorption compared to the standard OPC 53, which was only 300 square meters per kg. And OPC 53S has a higher C3A content compared to the normal OPC. So all these factors played a very important role in early strength development, and they provide a very durable mix with the high energy absorption values. Now, for those of you who are interested to read more, can refer to these professional publications from the technical associations, and they provide a guideline for use of fiber reinforced shotcrete. So the first one is Norwegian Concrete Association. The second one is the ACI, and the FNAR guidelines are there. And then there are ASTM guidelines as well. So this was all from my side. Thank you very much for listening to us. And over to you, Sanjay.
Yeah, I thank Mr. Jain and Davide for the time and quite an informative presentation on the technology about Shotcrete. And in fact, Mr. Jain, what information he gave about the fibers, that was really informative. Though we have been using fiber from a long time in India, but this kind of test equipments and practical aspects in the field that were quite informative. And so there are a lot of questions which people have asked and pertaining to the design and all that. So I'll just be taking one by one, and some people have even raised their hands. They want to go ask the questions. So first I just go with, I think what mixed design you showed during your presentation, there was some variation in the strength. Like the design, is it failed or it was under the limit? I could not see. If you can just describe.
This was the slide which we were discussing.
Yes,
so
yes.
Here the strength at 28 days was actually less than what we got without the microsilica.
Yeah.
So the requirement was actually this much only, and earlier we were getting more. And why we were getting more is because we were adding 450 kgs as a contractual requirement, which was somewhat misspelled in the contract. So actual dosage could have been kept much less.
Okay. Thank you. I think Mr. Sammelan Mukherjee must have got the answer for this.
Yeah.
And there's a person, Mr. Arianto Wibowo from Indonesia. He just wanted to ask the question about the cement which is used in your last slide, referring to ASTM C150, and if any of the similarity of the cement used between E53S maybe some and E53 in this presentation.
I think the only similarity may be the strength of the grade of the cement, because it is 53 MPa grade. 53 MPa grade is can be correlated to all the international available cements. But more important is the fineness of the cement, which may not be matching with the one mentioned in the ASTM, and as well as the other aspects like the fineness and the early strength requirements. Those will not match. So this is the cement is not available anywhere else also, and
okay.
Yeah, finer cement will definitely help in strength.
Okay. And there was one question from, okay, the name is not clear. How much is the waste of the Shotcrete materials usually in the tunnel? I think it is mainly related to rebound, I would really
Yes,
good
it is mostly related to rebound, and some part is usually left over in the hopper in the after the end of the application. So this rebound, as we discussed in the presentation, this was somewhere around 5 to 15% is considered a very good application. But usually at our site, what we got was somewhere around 15 to 20%.
Okay.
Yeah.
Okay, I think Davide, there's a question for you. One of the person from the site, in fact, we work with him. So, why the chemical manufacturers does not mention the retention time and benefits for the additives?
Okay, of course, as we mentioned during the presentation, each mix design is unique. So it's very difficult to write on a technical data sheet talking about workability extenders or retarders, what is the ability of each admixture to increase the workability. So each mix design according to the cement kind, because remember that each admixture works on the cement. So depending on the kind of cement which is available or has been decided to be used for the particular mix design, test must be done. So we can have a very high reactivity for certain kind of cement and others with less reactivity. So we have to increase the dosage per kilogram of cement. So again, it's really needed to, as Mr. Jain said, to conduct a pre-trial test in order to assess what kind of admixtures, workability extenders, and so on must be used for the particular mix design.
Okay, and I just would like to add to this also, because since we have been involved in a lot of additives in India in various sites, a same additive may work very well in a region in north and may not work in a similar mix design in the south. Because what Davide told that it all depends upon the clinkers, the source of the cement, the aggregate sourcing from where it is coming. So sometimes we have to really modify the additive so as per the local mix design. And generally what happens is, like in a technical data sheet, we mention the dosage limitations, like from 0.5 to 1% or 1.2%. But it can vary, like maybe plus minus 2-3% also, depending upon the temperature and the aggregate condition. Okay, and just a sec. Rupesh, I think he was involved in the Statue of Unity. Any experience with ultra-fine GGBS in place in used with in replacement to microsilica?
No, I don't think we have not tried yet.
Okay. In fact, Mr. Rupesh, we have done one trial in Vizag with GGBFS. So the only issue is that came in because it was a mixed design mixed with GGBFS and microsilica. The requirement of slump retention for the Shotcrete was around 2 hours, but the dosage of the additive really was a big task for us, and we have to modify a very special kind of additive, a high-end solid content additive for that particular mix design. So that we have done in one of the projects in Vizag only, and that was for Shotcrete only. Okay. Okay, Mr. Thak, in your mix design, you have mentioned the slump for 2 hours.
Yeah.
Is it initial or the final slump?
That is at 2 hours.
2 hours.
Yeah.
Okay, one more question for the fibers. How to make sure for the uniformity of the fiber spread in the Shotcrete?
Yeah, of course, there are two main points where the product, the fiber must be properly dispersed inside the mix. During the loading process, so depending on the kind of fiber, you can load the fiber during the loading of the aggregates, or you can preload the truck with the fibers and then with all the other components. And of course, during the mixing process inside the truck or the pre-mixer in at the batching plant, it's needed that all the fibers of good quality fibers are dispersed inside the mix in order to avoid balls or any kind of situation where there is aggregation of fibers without a proper concrete around. Because when you spray the surface, and especially when you carry out test on panels, normally, as Mr. Jain has properly shown, it's needed to cast at least 3 panels for each test, for each curing time. So out of 3 tests, the performances of panels casted at the same, more or less at the same moment, they should have a homogeneity in results. So you cannot have a variation of 50% passing from one panel to another panel. Otherwise, it means that there is not a proper homogeneous distribution of the fibers inside the mix design.
Okay. Mr. Jain, there is one question for you. Somebody is asking about the quality of fibers as compared to the steel, and because there are a lot of fiber available now internationally and locally. So how can we really select the fibers? Is it some length, aspect ratio, or like quality? What like, or like some, like they just wanted to ask this kind of thing.
Yeah, so this is actually to be looked into the right dimensions. Firstly, the fiber quality. We come to the fiber quality. So fiber quality has to be maintained as per the declaration of the manufacturer. And usually the international manufacturers have a declaration of performance. We call it the DOP. So if we are using an international manufactured fiber, we should ensure that it comes along with a DOP of the performance of the fiber. The second aspect of the question relates to the way we are mixing the fibers in the Shotcrete. So when we are mixing the fiber in the Shotcrete, we have to ensure a certain performance of the mix as such. So can you just repeat the second part of the question? I think I got it wrong.
Yeah, length, aspect ratio, and how you really, like, there are so many sources of the products available internationally and locally.
Yeah,
so generally when you, and trials are not that easy, what is mentioned. So how you would really, first selection of the fibers really come into the picture?
So usually the length, when we talk of the steel fibers, so the steel fibers cannot flex because they are rigid, and the nose dia really puts a limit on the length of the fiber which can be used. But that limitation is not there with the PP fibers. So usually the standard formula is that the more the L/D ratio is, which we call as the aspect ratio, the more is this ratio is, the lower will be your dosage and the better will be the output. But this is not a uniform statement, so it has to be tested and tried every time when you're doing it on your project site. There may be many number of manufacturers, but to compare different manufacturers, you have to actually carry out the trials on site. So I guess that there is no escape from trials.
Okay, okay. And there's again question from Mr. Arianto Vibovo. I think it must be some to you only. Based on your knowledge and experience, is there any correlation between FNAR panel test and round determination panel ASTM test for the 1000 joules in FNAR equivalent to how many joules in ASTM RDP?
Actually, in the ASTM circular panel, it requires you to have 40 mm deflection, and then you capture the energy absorbed in that panel. And in the square panels, it is actually 25 mm deflection, and then you capture the energy. But there is no correlation as such. I don't think it has been tried, and the correlation also does not serve any purpose. So it is more of a regulation, which country you are in, what are the specifications of your contract. If they say it is a round panel, then the energy has been defined as per the round panel, and that's it.
Okay. Davide, how much chloride content should be good for accelerator? And if there is wire mesh in the Shotcrete layer and core extraction becomes hard, or any suggestion? I think Mr. Jan, since has worked in both the cases in India, he can also let us know. Like in the wire mesh case, the core is better or the fiber base.
Okay, David, okay, to answer how much chloride content should be good for accelerator, I'm not really aware of what kind of limit should be about chloride. What instead I can answer is that if the project expects the use of wire mesh instead of structural fibers, of course, the extraction of course it's not easy as with fibers, but you can achieve it. So with the let me say up to date equipments, you can core also the steel, but I think Sumit can answer better.
Yeah, as far as core extraction in wire mesh is concerned, we have done it at our site. It's not a very big issue because usually spacing of the wire mesh is 100 by 100 or 150 by 150, and the core which we are extracting is 100 dia of cylinder. So usually we intersect, very rare to intersect the joint of the wire mesh. But yes, when it intersects, there is a slight noise, and the wire mesh, because it is not that thick, so it usually does not create any big major issue. But one has to definitely check the sample which has been extracted. So if there is any interference, then we have to push the next hole accordingly into the wall.
Okay, one question, Davide, can you recommend some internal curing agent, and when is the time suitable when it can be used? I think it can be used at the batching plant only.
Yes, the internal curing agent must be placed inside the mix design. Normally are recommended and useful when you expose your shotcrete to heavy heat, like an external with a heavy ventilation, so there could be some problem with shrinkage cracks. But in let me say normal tunneling situations, the internal curing is not necessary. I just want to spend one word on the fact that ITA, International Tunneling Association, is close to give to the market some guidelines about the fiber reinforced concrete for permanent application, so not for only for let me say first lining during the excavation of the tunnel. So all the subjects that we described, of course, they become even more interesting when we want the final layer of shotcrete to be the permanent one and not only as a temporary one.
I think somebody raised the hand. Let me see if the participant is still there.
Meanwhile, you are looking to answer the chloride content must be below 0.1%.
Swam, some lady Meena Khonde wants to ask some question. She has raised the hand. If you can put her. Okay, Yogeshwar Singh and Shayo Prasad. Swam, can you put Yogeshwar Singh?
I have already allowed them to speak. They can unmute and speak.
We can ask the participants to actually write down because it will be much faster.
Yeah.
Okay, Mr. Singh, in case you can put it online, that would be better. Otherwise, you can ask also. We have unmuted you. Okay. Anyhow.
Do we have some more questions from the other social
No,
media?
sir, I think questions. There was one question from the cement manufacturing pertaining to the C3S content, and do we need to use SRC for the shotcrete?
Do we need to use what for the Shotcrete?
SRC, sulfur-resistant cement.
That will depend on the exposure conditions defined in the contract. So if the exposure conditions are they are pretty much severe and very severe, then depending on the regulation, whichever is being followed, we have to use the required cement type of cement.
Okay.
It's not a general practice as such.
Okay. Okay. I think if anybody has got further questions, they can write it on the chat box, or I would like to tell you, like, you can send the questions through mail also to our marketing department or Mr. Subodh also, and to the concerned speakers also. There's no problem. You can send it. We will be pleased to answer the same. And once again, I really like to thank Davide and Mr. Jan. And Davide from Milan really took the time to give a webinar on this subject. And Mr. Jan, who has been like at Uttarakhand for this prestigious project of the government. So he was quite informative in as per the practical site application. So I just leave the like if Mr. Jan and Mr. Davide, they can say something and we can close the session.
I would really like to thank all the participants who joined us today to attend this webinar. And these were just a few of the experiences and knowledge which we could have shared with you. And there may be certain data wrong in this presentation, but it all depends on the limitations to which we were exposed when we were carrying out these tests. So one should not really go by the data, but should go by the spirit which was being discussed in the presentation. And the most important thing with the Shotcrete is actually to test it in the environment in which it is to be applied. So initially, when we are starting any project, the environment is not there. The application has to be done inside the tunnel, and the testing starts outside the tunnel, and the things go wrong at some point in time. So we have to take care of the environment in which we have to apply, the substrate on which we have to apply, and the machine which has to be used. Because even if you do a test trial outside the tunnel with a machine which is not to be used during the application, then there is no point in doing out that trial. So the operator, the machine, the mix which has to be used inside the tunnel has to be tested outside the tunnel. If you test it on a different set of parameters, then there is no use. You will never get what you wanted to get or what you would have achieved outside. So with those points, I'll just conclude whatever I wanted to say. And over to you, David.
Yeah, again, me too. I want to thank you, all of you, for the attention for this webinar. And yeah, keep on also testing new solutions, new materials, because it's the way to improve our industry. So do not be afraid on testing, as Mr. Jain has pushed in his job site, to find out a new solution for savings or for having better performances. So keep our email addresses as a reference, and please feel free to write us for any further questions. Thanks a lot.
Thanks, Davide. Thanks, Mr. Jan. And thanks all participants. And in the end, I really wish everybody to be safe and sound. And let's hope we get out of this pandemic situation as early as possible. Thank you. Thank you.